Welcome to Spring LIB.
In this exercise, we're going to be talking about circular motion and elastic force. So I'm going to review these topics. First, consider that we have a particle undergoing circular motion. The acceleration of this particle can be decomposed into two components. One of them is the centripetal acceleration, and the other one is the tangential acceleration. The centripetal acceleration accounts for the change in direction of the velocity and is equal to v squared divided by r. V is the speed, r is the radius of curvature, while the tangential acceleration accounts for the change in speed and is equal to dv dt. Now, regarding elastic force, consider that we have a spring attached to a certain block. The block has a mass m, and the spring has an unstretched distance, length actually, that I'm going to call d0. Now consider that the spring is then stretched to a length d. And we ask ourselves, what is the force that the spring exerts on the block? And the answer is that the force is equal to minus k times d minus d0. The minus sign here is just to show that the force is pointing in the opposite direction as the stretching, so it's pointing in this direction here. Okay, so now we have everything we need in order to solve the exercise. So what we have is a cylindrical plug that has a mass of 2 kilograms that's attached to a spring that has an elastic constant of 14 pound force per feet. The end of the spring is 3 feet away from the center of rotation, and the system rotates with a speed v of 15 feet per second. Okay, we also have that the unstretched length of the spring is 0.5 feet. And our goal is to determine what is the force that the spring exerts on the cylindrical plug G here when the system is rotating with a speed of 15 feet per second. Okay, so what I'm going to do is, first of all, draw the force diagram on the cylindrical plug. So this is a cylindrical plug. The force diagram is, there's, of course, the gravitational force pointing downwards and the normal force pointing upwards. They cancel out, so I'm not really going to bother about them. But pointing to the left, we have the elastic force F. And as I said, the elastic force is equal to the elastic constant times d0 minus d. Notice that for the force to be pointing to the left, the spring must be compressed, okay? So the displacement of the spring is in this direction here, and the force is in the opposite direction, meaning that the force is pointing towards the center of rotation. And we want the force to be pointing in this direction because the block is rotating around the center of rotation, and we know that the acceleration is pointing towards the center of rotation. Okay, so we know that the force, this total force in the horizontal direction is the elastic force, and the force must be equal to m times the centripetal acceleration, which is v squared divided by the radius of rotation. And notice that the radius of rotation is 3 feet, which I'm going to call L, minus the length of the stretched spring, which is d. So we have L minus d. So we have to solve this equation here. K times d0 minus d is equal to mv squared divided by L minus d. Our goal is to solve this equation for d, so we know that what is the length of the stretched string, and with it we can find what is the force that the string exerts on the plug, or the spring exerts on the plug. So we have d0 minus d times L minus d is equal to mv squared over k. So what we have is d0L minus d0d minus dl plus d squared is equal to mv squared over k. Our goal is to find what d is. So I have d plus d times minus d0 minus l plus d0l minus m v squared over k is equal to 0. Now, we can use Bhaskara in order to solve this for d, so we have that d is equal to minus b, that's d0 plus l, plus or minus the square root of b squared, minus 4 times a, which is 1, times c, and that is d0l minus v squared over k, divided by 2. Okay, so notice that if we choose the plus sign, the plus solution, then d is going to be greater than d0, and in fact it's going to be greater than L, and we of course we don't want that, because the value of the stretched, the length of the stretched string cannot be greater than the radius, actually the length L here in the figure. So let's use the minus solution. So we have d is equal to d0, that's 0.5 feet, plus L, which is 3 feet, minus the square root of d0 plus L, that's 3.5 feet squared, minus 4 times d0, which is 0.5 feet times 3 feet, minus m, that's 2 pounds, times v, that's 15, v squared, that's 15 feet per second, squared, divided by k, and k is 14 pound force, and 1 pound force is 1 pound times 32.2 feet per second squared. Okay, so d is equal to 3.5 minus the square root of 3.5 squared minus 4 times 1.5 minus 1. Of course, everything must be divided by 2. I'd forgotten it up here. So d is equal to 0.15 feet. So F, the force, is 14 pound force per feet times 0.15 feet. So the force F is equal to 4.9 pounds, which concludes our exercise.